So welcome back, guys. Today our topic is fluid mechanics. So already I have completed Pascal law, Archimedes principle, Bernoulli's principle, and its applications. From last and important topics I have discussed. So the today more important and basic concept of fluid mechanics. First concept. So that is pressure. Concept of pressure. First, I mean this is the starting video. So we know pressure is equal to force by area. This is a scalar. That means we'll call it as a pressure. Pressure because it have direction and magnitude, but not following the vector law. Second order of vector we'll call this is so pressure. And SI unit is Newton by meter square. It also considered as 1 Pascal. Pascal scientist name we are honoring by taking as pressure unit. So other units of pressure is equal to atmosphere, means barometer experiment. Torricellian barometer we call this is. So 1 meter length of tube you have to take, full with mercury, close with thumb, and take a bowl of mercury and immerse in that. So you will get the mercury rises to the 76 centimeter height and it will stop. That means atmospheric pressure is only means the atmospheric pressure is stopping the fall of mercury from the tube, right? So that which is equal to 76 centimeters of mercury are okay. So that is only here you cannot take this is vacuum only, nothing is there here. Therefore, this is called Torricellian vacuum. Only 24 centimeters of mercury came down. Remaining 76 is standing here only. That means atmospheric pressure which is equal to the H rho 76 centimeters of mercury. So that is atmosphere. So here you can ask why mercury only hard to take. If mercury density is more, the density of mercury is 13.6 gram by cc. So that equal to into 1000 13600 kg by meter cube. So it is very large. That is why the mercury stand at 76 centimeters. If I have taken water means it will become the length of the tube which is filled with water required more length. That is the reason we are using mercury. Some other applications also there. That is chemical properties of mercury and other liquids are different. It is easily visible, shiny, not stick to the walls. That and all. Another more density. So these are the points. Consider mercury as thermometric liquid and as well as barometer liquid pressure to measure the pressure of atmosphere. So now here 1 atmosphere equals 76 centimeters of Hg. If we substitute the values, so you will get 1.013 into 10 power 5 pascals. So that equal to 1 atmosphere is equal to, so 1 bar also you can write 1.013 bars also you can write because 1 bar equal to 10 power 5 pascals. So R something into tar also you can write, right? 133 tars, right? 1 atmosphere equal to. So like this you can write one tar is equal to 133 pascals. 1 tar is equal. So like that 1 tar equal to 1 millimeter of Hg. I want to convert it to pascals. So I'll get 133 pascals. So these are the units and calculation of pressure. Pressure is equal to H, F by A. Here F means thrust. So that is the fifth property of pressure. So I'll explain. Means the pressure is always considered vertical to the contact. The tangential force will not give the pressure. The pressure is responsible by only vertical component of the force. So here I'll explain, see that somewhere. So here if you take, this is the liquid in a vessel. So the force acting in the direction, suppose. So this liquid drop is not moving in a tangential direction. The force tangential force direction not act. So only the pressure is calculated due to the perpendicular force. That is why pressure defined as the force perpendicular to the surface, that is thrust by area, not tangential force. Due to the tangential force, fluid is not moves. The tangential force is not responsible to apply the force. Right. That one more property also I'll explain. So this is so first of all properties of pressure. So pressure is isotopic. That means in a static fluid, this is the static nature of the fluid, and we are studying the fluid statics. So means fluids are at rest. Means water in the vessel, water in reservoir. Example for fluid at rest, static rest. So now if you take any one cubic volume, this is the cubic volume like this. So inside the water, any small cubic volume, areas are same. So now this is in equilibrium. That means the force acting in all the directions is equal. In all the direction is equal. Forces are equal means areas are equal here. Each cube has same area. Therefore, force is equal to pressure into area. Pressure is also equal. This is isotropic nature of pressure. Means in all the directions in a static fluid, the pressure acting in all the directions on a surface of or a point is equal. This is also explaining Pascal, but their distribution of pressure is given by the Pascal. How the pressure is distributed from one point to all the points. But in isotropic nature of the fluid, the pressure acting on a point in the static fluid at any point, wherever the point is equal in all the from all the direction. That is isotropic nature. So pressure is uniform in horizontal plane. So consider here the static fluid in a beaker. So two ways I'm going to explain this one. Consider here A, B, C points on one horizontal plane. So this is the property true only in case the vessel is not accelerating. Vessel is not accelerating. If vessel is accelerating, so the pressure on this horizontal plane are not equal again. So now this pressure in this case static fluid, the pressure vessel is in static state. This is called equipressure line. Equipressure line, horizontal line. Why means, so we know pressure is equal to H rho g. A, B, C points are in the same height and density of the liquid also same. Therefore, pressure at A, B, C on horizontal plane is same. Otherwise, consider one ds element, cross-sectional area ds element of liquid inside anywhere. So not different inclination, horizontally consider, because we are discussing about the horizontal plane. So now on both the sides of this element, on this area of cross-section area of ds element, force is acting. F1 and F2 as shown in the figure. So these F1 and F2 are equal because this element is in equilibrium. F1 means pressure into delta area, pressure into ds. Ds is the small area of this cross section. So P1 equal to P2 I have proven. So whereas coming into pressure increases with depth and pressure decreases with increasing in height or decreasing in depth. Pressure decreases with decreasing in depth, increases with increasing in depth. So reverse, pressure decreases with increasing in height. Height means always measured from ground to surface of the free surface of the liquid. Right. So now here, just before concept, pressure is equal on the horizontal plane. But now three different horizontal planes I have taken. A, B, C. The pressure at B and pressure at C are equal because those two are on horizontal plane, equipressure line. Now A is the more depth than B and C, then automatically P A greater than B and C. That is very known. From the free surface, A height is more. So explanation C1s for explaining, consider a small element like a ds element here. So here pressure P1 and P2 are equal. So now in the HD here P naught on the P surface, P naught atmospheric pressure, the free surface. So here some P. At this point, pressure is P. So now at this due to this element, pressure is equal to dH into, this is the element of height, dH consider. So dH into rho g. So now integrating from 0 to h or h to 0. So now I am integrating from h to 0 means height is increasing, depth is decreasing. So that means h to 0 means height increasing, depth decreasing. Okay. Then pressure what happens we'll see. So here P I have taken, here P naught I have taken. Therefore integral P to P naught, varying pressure is P to P naught. P naught minus P is equal to minus h rho g. Then P is equal to, pressure at this point is equal to P naught plus h rho g, means more. P naught is equal to P minus h rho g. So at the point P naught is equal to pressure at depth point D point minus h rho g. So this will be very important. This concept, this point, pressure decreases with the height increases, pressure increases with the depth increases. So these points in manometric equation are very important. When you are writing the manometric equation, this property of the pressure is important. So remember that. So now thrust more than weight. Thrust means force, weight. Now thrust means force on area. Weight means mg. So here I have given weight equal to mg. M means volume into density. So here volume h minus h into area of this one and small h into capital area of this one. So it will come like this. The pressure is not considered the value mandal in the pressure only consider height of the liquid. This is the both are same liquid. Then how much height of the liquid is there from bottom? So that is H rho g into A is the pressure symbol. Pressure equal to H rho g into A means thrust. Thrust is equal to force per perpendicular area. That is. But mass is equal to H rho into shear, volume into density. All the liquid have same density. The volumes here volume and here volumes are different. That I am writing. Therefore, if you compare these two equations here, one is H rho into small a g plus rho g h into capital A minus A. Okay, capital A minus A. So this value. So it is anyhow the weight is more. The thrust can be greater than weight. So thrust can be greater than weight. Thrust can be greater than weight. Weight is thrust more than weight. Weight is mg and thrust is force perpendicular force. I very clearly have given one of the property of pressure, that is exerts the pressure, means fluid in equilibrium exerts the pressure right angle to the surface in the above. So here also pressure is equal to H rho g due to liquid column, that is gauge pressure also will call, I will give later, and area. So this is thrust on the bottom, H rho g into A. So here mg is the weight, that is equal to V rho g. So here capital H rho g into capital A, but here small a. By these two equations you can tell thrust can be greater than weight. One more property is the pressure seeks its own level. So it is independent on shape of the container. So that points I have written somewhere. See, pressure depends on height, density and G. So because the pressure is equal to H rho G. It depends on height of the liquid, density of the liquid and G, acceleration due to gravity. And independent on, the pressure is independent on amount of the liquid. I will give the examples each topic. Shape of the container, area of the cross section. So now whereas coming into that properties means that points explanation. So here I have taken, if you observe in general life also, so two limbs, two areas, different tanks you consider like this, two different tanks here I am taking. So in one of the small tank, water is falling. So after some time, if you observe, in both the tanks, the level of water rising equally. The smaller tank and the water is coming into the smaller tank only. Even though after filling smaller tank, the water will not go to the bigger tank. So both levels in the both the tanks will be raised equally. So this is 6 its own level. It is independent on shape of the container. The liquid occupies same height, even though container shape is different. When pressure is equally applied. So like this input water is coming. Now it will depend independent on amount of water C1's pressure. So now here in this example, I have taken same values. Values are same. Cross-sectional areas of these three vessels also same. When values are same, due to the different in shape of the container, the heights are different here. The occupying means here 1 liter of water I have taken in a different three containers. Because of their shape, the volume occupied is different. That means height is different. Base area is same. But shape is different. It occupies heights are different. Therefore, pressures are different here. So whereas coming into here, in this example, base areas are same but different vessels. Different amount is poured in those vessels to occupy the same level. Different amounts of water or fluid or liquid and pouring to the same heights. Automatically they require different amounts only. Even though the pressures are same. Whereas weight will be different. Because amount of water different, weight is different. But pressures are same. This is called hydrostatic paradox. Means different amounts apply the same pressure. Different amounts apply same pressure based on its shape of the container. That is called hydraulic paradox. So very important here after. Up to now, concept of pressure and how to calculate the pressure and properties of pressure explain. Once again, properties of pressures are isotropic, same in horizontal plane, perpendicular to the surface, pressure applies on the surface perpendicular, pressure seeks its own level, the pressure increases with depth, decreases with increasing height or decreases with decreasing depth. So these are the properties. And pressure depends on independent and different cases. What is hydrostatic pressure? Up to that, the basic barometer and S is SI units per tunnel over. The pressure in E tube shapes. So now if you see this one, so in the limb 1, one of the liquid is poured, and limb 2, another liquid is there. So in limb 1, the liquid height is equal to H1. In limb 2, another liquid height is equal to H2 is equal. One is density rho 1, another one is density rho 2. So according to one of the property of pressure, that is horizontal line, EQ pressure line for a static fluid, pressure on this line everywhere is constant. Means pressure at A is equal to pressure at B. So pressure at A we can find out. So P naught plus H rho G. If the P naught is added, P naught plus so gauge pressure is absolute pressure will call. Absolute pressure. So only P naught H rho G is there. That is due to the column of water. So this is called gauge pressure. So gauge pressure is due to only length of column of fluid. It is added by atmospheric pressure, absolute pressure at that point. So maximum cases will not take absolute pressure. In Bernoulli's principle also will not consider the absolute pressure because both the points are exposed to atmosphere. So there both the sides we can neglect. Now see PA equal to PB here. So that means H1 rho 1 G is equal to H2 rho 2 G. When the liquid 1 rho means liquid of rho 1 is poured in a limb left side limb, already there is a liquid right inside the tube that will be raised this side, this side. So initially somewhere the initial heights are not considered here. Only H1 is height of the first liquid and H2 is the height of second liquid. That only. Then H1 rho 1 equal to H2 rho. That means in this case H is inversely proportional to 1 by density. Means inversely proportional to density height. H1 rho 1 equal to H2 rho 2 or H1 by H2 is equal to rho 2 by rho 1. Inversely proportional to density. That point will come from that example. Now here in this example, so H1 is one liquid, H1 is one liquid, H2 is another liquid, the remaining is another liquid. So in one three liquids are there here and uniform cross section. So don't think about the diagram. That is the reason I have given uniform cross section. So when uniform cross section, how much volume is depressed in one limb, that much volume will be raised in another limb. In that no doubt. The volumes are equal, at the same way heights also equal. Where in the case of uniform cross section, by pouring the another liquid on both the limbs, so how much depression happen in one limb, the other side that much volume has to rise. If both the sides depression is happening, means the tube, the bend will be expand. Okay, na? Means expansion will happen. And here we have taken incompressible liquid setup. Means this liquid cannot be compressed itself. So this liquid cannot be compressed. So here by pouring the rho 2 liquid and rho 1 liquid, if rho 1 liquid has more density, this rho 3 liquid has to rise this side along with rho 2. Both rho 2 and rho 1 are more denser and both are compressing, means this will be compressed, right? That is not possible because we have taken incompressible liquid setup. Incompressible, immersible liquids also. They will not merge, right? So that is the property of in U-tubes, right? The liquids are immersible. They will not merge. They will not one and another they'll mix up, right? Like that. Incompressible and immersible. Incompressible means it has to expand another side or it has to compress another side. One side compressing means another side expands same value because uniform cross section. That point remember. So now here again, horizontal plane. This is the concept of horizontal plane. Pressure line for static fluid. 2 points we'll consider. You can ask me where I have to consider that. So now better anywhere. But here see, if I am considering example here, I am considering pressure line. Okay now. So the sides and all different, and you cannot tell. We cannot find out this relate this down acceleration. That is not, this line is not correct at all. I am unable to explain why not because see this liquid is here something and down something is there. According to manometer expression, maybe you can find out. Otherwise, all. So this point is exactly correct. Okay, this point. All liquids is matched here and heights and everything you can easily find out. So now see this is HEG and HEG is height H, here also height H. And rho 1 is H1 and rho 2 is equal to H2. So they can give this is total H2, no problem. Then X into H1, they will ask X value. H1, H2 they will give and X value they will ask. So now this is the formula at PA and PB both are same because PA and PB, A and B points on equipressure line. Next example here. So here if you see H1, H2 and H3 means X, rho 1, rho 2, rho 3 liquids are have different heights in the both the limbs as shown in the figure. Now coming into here, cross section, uniform cross section. So this side one liquid, the glycerin, the density of glycerin here, the glycerin poured in the left limb, and in the right limb there is I. So height of the glycerin is equal to 10 centimeter, and the density of the glycerin is something, the values if they have given means we'll substitute. The density of glycerin they have given 1.3, and density of oil kerosene means 0.8. Oil means kerosene, that is 0.8, and here mercury this is. So when glycerin poured in the left limb, the mercury and oil are staying like this with respect to heights. X height of oil, x centimeter is the height of the oil poured, and 10 centimeter distance is glycerin here, right? This is the glycerin. So now this is mercury. So here is mercury, this is mercury. This total is mercury. So here this is kerosene, you can go. So now this is the line, equipressure line. Now we know PB and PA, 2 points I am taking. The pressure at B, pressure at A. The pressure at A due to mercury and I. Pressure at B due to only glycerin. So you can take here also equipressure line, not a problem. Because this one and this one get cancelled. This value and this value, both are same liquids, so get cancelled. So this also you can take equipressure line. But above, so here you cannot take the equipressure line. This is wrong. This is equipressure line not. Okay. If you are taking this one, then this value they have to give. This value is how much you have to find out. So they have given this value we don't know. So that value is equal to here. This is density, right? Taking. So in monometric equation, maybe we'll get this expression going from one point to another point down. Down means negative, up means positive. Down means positive, going up means negative. That will explain in monometric explanation. Maybe there it will be suitable, I think so. But by this time, take equipressure line properly. That means all liquids should, means all length and liquids can give the clear expression. Then only consider like that, consider equipressure line in this case. So on the equipressure line, 2 points you consider. There find out the pressure. By seeing the diagram, you have to consider it, right? Now this is very good example. This is up to now we discussed they have given already heights, liquids, different liquids heights, how they are. But here, so there is a liquid initially to the height. This is the initial height of the liquid. So in one of the liquid, one of the limb, left limb or right limb, that is your wish. I have taken left limb. In the left limb, so I poured another liquid of density rho. So then it is compressed. The volume is compressed. The same volume is raised here x. So this is of density liquid rho is raised on the other side. So now here how much length is depressed? The same length will be raised here because these two are uniform cross sections, same cross section. So how much depressed? The same height will be raised. So now initially there will be a y length height. Initial length of the or height of the liquids in the limb is equal, both the limbs is equal to y consider. So now according to equipressure line, so I have taken here equipressure line. So this is h height is given. So h into dz at this point, h into dz is equal to 2x into rho g. So here to here 2x. This is 2x will come, here to here 2x will come, 2x into rho g. So these are the values you will get. So if not means like this you can go. Initial height is y I will take. Initial height is equal to y. So now this will be h distance is given. So now h dz plus. So this is some x. That means this x is equal to h minus y will come. H this is the length of this one is equal to here. How much length will be raised? This is y minus x. Rho g is equal to y plus x into rho g here. Now this is y. So y plus x, y. So this here, this is equal to y minus x. This length. So now you are substituting now, you get answer. So here the equipressure line I have taken here. So up to h there is a up to h there is one liquid poured. Then initial level x is the depression. So now this length is equal to y minus x, and another side is equal to y plus x. In the y minus x length, density is equal to density of the liquid only. So in h length, density is equal to d. Equations PA and PB. So yeah, same thing you get. Now if two limbs are not same cross section, so this is important. Not same cross sections means the volume depressed is equal to volume raised, but the length depressed is not equal to the length of the raised. X into A is the depressed volume. So other side y into A. This is x into small a I can consider here, and y into A. So this x depression, the length of this liquid density d, and y rise is density of this fluid. Density of this fluid, right? So already which is there up to the initial fluid, that will be rises this side. So the this value x value is occupying by the density of d. This x value in the limb, left limb, will be raised in the right limb. So volume depressed in the left limb is equal to volume raised in right limb. So volumes only means x into area, y into area. So now x and y relation will get. Now consider equipressure line. So equipressure line, this I am taking as equipressure line. H into rho 1g or dg. So here rho 1 is given, liquid density rho 1 is equal to x plus y into rho 2g. Rho 2g initial liquid. Rho 2 is the density of initial liquid. Rho 1 is the density of liquid poured here. So this is the answer. Right? Now, coming into manometer. In case of manometer, the manometer is used to measure gauge pressure of liquid only, not gases. Gas pressure cannot measure. And two types of manometers are there. One is simple manometer. Simple manometer is so like this. Like this. So H rho g is equal to here A and B, pressure B, which is equal to pressure A, because A and B are on same horizontal line, equipressure line. Therefore H rho g. So because of this fluid here, either gas or liquid, is there inside manometer, bulb of the manometer. So I poured one liquid, it will be raised up to this. So the remaining and all here fluid. This is the fluid liquid poured from outside. So H rho g is the pressure of gauge pressure of the liquid considered in manometer, in limb of the manometer. So that equal to PA and the points are same. That is simple manometer. So now another one is U2 manometer. This is considered like this. First of all, I'll explain about the manometric equation is what. So manometric equation, very simple manometric equation. Any 2 points consider. So here point A, here point B. So whatever the densities of height, whatever the liquids here. So starting from B, then PB. So going down, right? So this is some H1, one liquid of density. Therefore, H1 rho 1 into G. In horizontal, there is no change. Again, here going up, right? Minus H2 into this can be different density or same density. That is your rho 2 into G is equal to PA. Therefore, PB minus PA is equal to H2 rho 2G minus H1 rho 1G. Same density means we can write H2 minus H1 of rho 1G. See now, correct or not sequence? This is H2 minus H1 only na. So pressure here and here same only na. Pressure at C and pressure at B same. So therefore, we can write the gauge pressure is equal to H2 minus H1 of rho into G if both the limbs have same liquid. Different liquid means this is the answer. Okay, this is gauge pressure. If you want to find out absolute pressure at any point, P naught add. If I want to find out the absolute pressure at A point means this is the answer plus P naught I will add. Right? This is H rho G is gauge pressure. Remember, due to the height of the column of fluid gives gauge pressure. Adding P naught means absolute pressure. See here one more equation. This diagram you take, this diagram. So now H1 is the fluid have density D in manometric liquid, that is. So that is D density. So I pour a water in the U-tube or a liquid of density rho. So up to H2 and H1 as shown in the diagram, the pressure is now equalized. So here you consider this is equipressure line now. So coming into point A to this point B I will go. This point B means P naught. So write the manometric equation first starting from PA and here going down, it is going down plus H1 dg. So in the H1 height, liquid is D, therefore H1 dg. Now here and here same height, same liquid, so cancel. One is positive down and here negative. If you can take this is also equipressure line, no problem. Then one more. So this is some X rho g, positive X rho g and negative X rho g. Cancel that, no problem. That's why I'm not taking. This is the equipressure line I'm taking. So PA plus H1 rho g. So now coming into here, I'm going up again. So this is H1 minus H1 rho into G. Here H1 into D into G. In this left limb, in the H1 height, density of fluid in the manometric fluid. Here this is the liquid poured, H1 rho G. Now again going up minus H2 rho G is equal to P naught or PB. So now PA minus P naught. So this is PA minus P naught means gauge pressure. So if P naught will go that side, PA, only PA means absolute pressure. Right, PA minus P naught is gives now gauge pressure. So H1 plus H2 rho G minus H1 into dg. So this is answer. I hope you understand manometric liquid. So here I have given see different diagrams. So now, if in a above diagram, the liquids are arranged like this. Up to here only the liquid is stands. The liquid stands in the left right limb up to here on. So in that case, so point A and point B or P naught. At point B is P naught, open to atmosphere P naught I can take. So now PA going down plus HDG. So now if you see here, you can take this is also equatorial line, no problem. If this is H2 is given, total H2, this will become, this side will become H1, right? This side will become H1 only here, anyhow. Okay, now we can take here also, this is also equipressure line. So then PA, so this is H2 minus H1. So now PA down H1 dg going down from PA going down H1 dg and now going up, that equal to this is H2 minus H1 into rho g. H2 minus H1 into total is H2 minus H1 rho g is equal to P naught. Right here getting down and going up. So simple, this is H2 into rho g I can write. So if you take here equatorial equipressure line, so this is H2 minus H1 plus H2 into rho g will come. Okay, plus here plus H1 in H2 into the rho g. So if you take here equatorial pressure line. So now H2 rho g minus H2 rho g get cancelled. Therefore PA H1 dg. So plus H1 rho g is equal to P naught. So therefore the PA is equal to P naught minus H1G into D plus rho. Okay, this is. So application of manometric liquid. Manometric equation for finding the pressure, gauge pressure of a liquid by using the manometer. So now in this case, I am trying to tell both manometric pressure and the horizontal plane concept. So 2 points, the pressure difference A and B they are asking. And if you know pressure difference A and B, then theta also you can find out. What is angle theta here? And the length of A tube and A to B tube and B to this 1 point H is given, not length is given. And densities are given differently. Rho 1, rho 2 and rho 3. You can check here. So now if you see here P naught. So first manometric liquid will write, manometric equation will write. So starting from 1 P naught at P1 you can take. So coming into B down I am coming H rho 2 G down H height. So H rho 2 into G. So now B2 up I am going PA, therefore minus. So this height is given H, that's why H rho 2 G I have. So here height is not given, length is given. This length not, height only have to consider here. So that equal to rho 3 GL sin theta minus. So again coming down, therefore plus the rho 1 GL sin theta. H is equal to rho 1 GL sin theta is equal to again P naught here. So this is manometric application, manometric equation application. Here it is clear, I think. So from 1 I started. You can start from any point, no problem. So this is. Now general equation since. So at B, PB is equal to P naught plus H2 rho g. And PA is equal to PA. PA means height point. So height increases, pressure decreases, we know. Therefore PA is decreasing. P naught minus rho GL1 sin theta. Okay. So now from this PA and PB again. PA to PB I am writing equation. PA rho GL sin theta is equal to PB. PB is more than PA. Solving these three equations, I will get the same equation. And from these equations, H rho 2 is equal to rho 3 will go that side, positive, and rho 1 is negative. Rho 3 minus rho 1 GL sin theta. Then sin theta is equal to H rho 2 by rho 3 minus rho 1 into L. So H and L both are same means, then H and H get cancelled, rho 2 by rho 3 minus rho 1. So this is answer. Pressure difference also you can find out. PA minus PB is equal to rho 3 GL sin theta. So that is. So this is about pressure in E-tubes, different cases, and application of manometric equation, manometer measures. Now coming into fluid in uniform aeration motion. Means aerating fluid. The vessel is aerating. So when vessel is aerating, the fluid rises opposite side. How much height is rising, that much height depressed also. So here I have taken points A, B, C. 3 points I have taken here. A, B, C. So now this line is here free surface line will call. And this line is also called as equipressure line. I am going to prove that equipressure line. If you remember, I said the equipressure line is horizontal. The pressure is same at horizontal, one of the property of static fluid. But here it is aerating. So pressure at A is not equal to pressure at B. Even though those 2 points on same horizontal plane, but pressure at A is not equal to pressure at B. Because it is aerating. That is one point. So it is very clear. The C is in the distance H2 and B is in the distance H1 from the bottom. Height H1, height H2. H2 is more. Therefore, the pressure tan theta here from this tan theta is equal to, from the diagram, H2 minus H1 by L. L is the width of the container. Right? So now, general free body diagram equation, NLM, MA is equal to pressure difference into area. MA is equal to net force, that equal to pressure difference into area. So your pressure difference between A and B points. So that equal to H2 minus H1 into rho G pressure into A. From this you can find out H2 minus H1 by L is equal to A by Z. I know already H2 by L, H2 minus H1 by L is equal to tan theta. For tan theta equal to A by Z, theta equal to tan inverse A by Z. So now, so this is H distance is raised to one side opposite to the aeration. The same X distance is depressed on the other side. X distance volume of the liquid depressed and the X distance same volume is raised on the side. So therefore total H2 minus H1 will be 2x. By L is equal to A by G, then 2x equal to A by G. This is H. H is equal to AL by G. So this will be useful when I am going to prove PB, means BC lines are equipressure line, equipressure points. I want to go to prove there this point will be helpful for us. And here the pressure at a point on parallel line to the inclined free surface are equal, means equipressure line. So now there is a one A point is there, this line, which is parallel to equipressure line. So these two lines are equipressure line, and these lines, parallel lines, all parallel lines are equipressure lines. So now this equipressure line and aeration is making the direction of equipressure line, and aeration is phi angle. This is angle between equipressure line to the aeration, that equal to 180 minus theta. Phi equal to 180 minus theta is equal to tan inverse A by Z according to our concept from the above diagram. So this here again I have given diagram, it's clear. Now this line is equipressure line. C and B are same pressure. So this point. And so along the direction of aeration, the pressure decreases. That means PB is less than PA. PA is more. Means opposite, pressure increases. The pressure increases opposite to the direction of aeration. In opposite direction of or to aeration, the pressure increases. That means at A point pressure is more than B point. That means PB is equal to PA minus rho AL. That equal to PA is equal to here. PA is equal to PB plus rho AL. That means PA is more than PB. So how much PB I will tell, right? Right. So now from this equation, PA is equal to here PC plus H rho G. From the diagram, PA is equal to, this is H2 minus H1. PA equal to PC plus H rho G. And the same way PB is equal to PA minus rho AL. So PC and PB are equal, I want to prove. This way I want to prove. Now subtract these two equations. So it will come this side minus PA. Add these two equation. PC minus PB will come here. PC minus PB. H rho G minus rho AL. PC minus PB. H rho G minus rho AL. So here before I said, so tan theta equal to H by L, that equal to A by G. AL is equal to GH from here. So this value will become 0. HG and AL both are equal according to aerating fluid. So PB is equal to PC. That means the pressure at B is equal to pressure at C. So this line is called, the inclined line to the free surface is called the equipressure line. Parallel to that free surface line, all are equipressure line. Pressure is same. So calculation of pressure at A point, already here this is enough. So otherwise like this you go once. So this is the point you can consider. So this is perpendicular distance capital H consider. So there we can write pressure at that point is equal to, so pressure at the A point is equal to, in terms of capital H, that I can write. So actually pressure at A is equal to H rho G plus PC I have taken. So here also pressure is same, PC and PA, right? So H I can write as, so this small h I can write as, this is capital H and a theta angle if you take theta. Then H is hypotenuse, theta is adjacent side, therefore secant theta will come. Therefore hypotenuse is equal to H into secant theta. Secant theta is equal to, we know, secant theta is equal to hypotenuse by, means small h by adjacent, reciprocal of cos theta. Therefore small h is equal to capital H secant theta. So capital H secant theta into G. So now secant, from the triangle, we know tan theta is equal to A by G. So this is root over A square plus G square. So now secant theta is equal to again root over A square plus G square by G I can write. So now if you substitute, therefore PA is equal to, in terms of capital H, HE root over A square plus G square, that's enough, plus PC. So PC and here also PC only will come, because equipressure line, that is PC only will come, get cancelled. PA is equal to H into rho into root over A square plus G square. This is root over A square plus G square is also taken as G effect. So at this point, G effect 2. This is acceleration and this is G. So in the direction root over G square plus A square. So G effect 2. Otherwise, secant theta, cos theta components you can resolve and you can find out. PA is equal to HPC plus HOG. So that is, means pressure at a point perpendicular to the distance from the free surface. So this is the formula. Perpendicular distance is H, capital H, and theta is 2H by, or H is equal to theta equal, given me tan inverse A by G you can apply, otherwise tan theta equal to A by G, or if you not given, here you can go with it. Tan theta is equal to this formula, 2H is equal to AL by G also you can say, like that. So this is related to aerating fluid. So now rotation of the fluid vessel. The vessel is rotating. So I will start with the simple one, that is the rotation of fluid in a cylindrical tube vessel of length L, and both the sides are closed. So one end of the tube is rotating with angular velocity omega. So now, so here pressure, this side the pressure P2 will be more, this side pressure will be less, P1, because the centripetal force acting towards the axis, right, towards the center of axis. So here center is equal to radius is equal to x. Therefore I can say A equal to omega square into x, or omega square from that. So now what I will apply means MA, or MA is equal to, means DMA is equal to dm into x omega square. So this is force. The force is equal to here the difference in the pressure, so that equal to dp into A. So now dp into A is equal to force dm into x omega square. So here dm I can write as dm is equal to volume into, therefore A into delta x into density. So that equal to A, the rho x means omega square x dx. So A get cancelled. So the change in pressure is equal to, at that point, the rho omega square x dx. So now 0 to P the pressure, or this is the point PA and PB. Therefore the change in pressure from A to P, A to B, PA minus PB, or PB minus PA. So PB minus PA, or 0 to P. The P is at B. At B point pressure is P. At A point pressure is 0. So now the P is equal to integral here, this is 0 to x. Okay. at this point. A point x is equal to integration x equal to 0, limits of x, and it is L x to the b L, that equal to rho omega square x square by 2. So that equal to here 0 to L. So that equal to 1 by 2 the rho omega square L square. This is answer. So pressure means P is increases away from the axis of rotation, decreases towards the axis of rotation. So now here it is not closed. One end is not closed. So like this is given. That what happened? This end is connected to one tube here. This end is connected to one tube. Then the liquid rises. So if liquid rises to H height, then the same amount of liquid, because the cross sections are same, right? Same gap has to come here, right? So this volume A into H volume is raised this side, and it is rotating with the angular velocity omega one side. Same as previous problem. Consider delta x amount, delta x element. It's d mass. Dm mass is equal to small mass dm is equal to same area into delta x means dx into density. So now pressure integrating means here the ma means pressure into area. So dm into a is equal to dp. Here the pressure is equal to in this direction P2, that is P plus dp. This side should be more and this side will be less. Yeah, because net force is like this. That's why this side is more. P plus dp. Subtracting the dp is equal to dp is the change in pressure between these 2 points into area is equal to similarly dma net force, right? Ma is equal to omega square into x. X is the radius here. So now a dx into rho into a. This is m into a is equal to omega square x. A and m. Now this cross section area get cancelled. So integrating from, so this is point B and point A to point B. So at point A, PA, dP. So A to B points is equal to, so now the rho omega square is common. Now integral from where to where? So this x is changing into h to the total length L. Therefore h to total length L. So this is the length of the limb is equal to length of this container equal to L. So h to L x dx. So that equal to rho omega square by 2 into upper limit L square minus h square. So now PA minus PB. Limits are there now, plus C should not take. So now PB minus PA is equal to the rho omega square by 2 into L square minus S square. So now PB is equal to, I can substitute, PB is equal to, according to this diagram, PB is equal to H rho G. At PB is equal to, so this is PA plus rho omega square by 2 into L square minus H square. So which is equal to H rho G, right? At PB, this is the height H means H rho G is the pressure at B, right? 1 minute. So now this is one model. For example, pressure at C I want to find out. The pressure at C is equal to, pressure at C is equal to pressure at B minus H rho G. Because PB is equal to PC plus H rho G. Na? Pressure at point B is equal to PC plus H rho G. So now that I substitute means you will get PB value already know PA plus that is substitute. So another model here. So here 2 more models. If you see, so initially the liquid taken in a beaker or in a vessel like this to the height y. This is y height. Y is the initial height of the fluid. So now the middle rotating, the fluid, this vessel is rotating the axis about the axis given, and this axis have radius r. Means this is diameter is d, that the radius of this vessel is equal to r. So now consider here a dm. The similar here, dm is equal to, we know very clear, that equal to a into dx rho, and here pressure difference here if you see, so this is the normal reaction acting along this direction, and this element is moving in circular path, horizontal circular path with radius x considered. So therefore a is equal to omega square x. For understanding purpose, in all the cases x I am taking as a radius. So now x varies, right? And here sometimes the liquid can come to y minima is equal to 0, like this also can. Y minima will become 0. That means x equal to 0. So this point also x is equal to 0. Y minima point x equal to 0. Now if you see reaction force and here theta you consider, then r cos theta is equal to its mg, and r sin theta is equal to m r omega square according to horizontal circular concept, mx omega square. So now tan theta is equal to omega square x by g. So here tan theta from the diagram, so the y is varying, right? The theta will be varying, tan theta. So dy by dx with respect to x and y, the slope, tan theta is slope here, dy by dx, the change in y with respect to x is equal to omega square x by g, I can say. So that will be, so dy is equal to omega square by g into x dx. So now we are integrating the y values, y limits are y minima to y maxima. You can take y1, y2 also, no problem. So therefore, so now integrate, integral, then x limits are, so x limits are 0 to r. So x is 0 to radius, maximum x is radius and minimum x is 0. So now y1 to y2, y1 is taken as minima and y2 I have taken as maximum. So y1 to y2 dy is equal to omega square by g integral 0 to r into x dx. So that equal to y2 is equal to omega square r square by 2g plus y. So now if we see, so for example, this is y minima, means the liquid is like this, you can consider, not a problem at all. So this is liquidized. This is y maxima, this is y, right? Up to here y. So this is y minima, y maxima. So y I want to write in terms of y maxima and y minima. So now this length will become y mag, this length, see, this length is equal to y maxima minus y. So this length is equal to y minima minus y minus y minima, right? So therefore, so y, this is, so this point will be half of the y maxima and y minima, y minus this length, y2 minus y2 plus y1 by 2, y2 minus y1 by 2. So y is equal to y2 plus y1 by 2. Otherwise, y1, so we can get that value y1 plus, up to y1 means minimum distance y1 and y2 this is. So y1 plus, this total value is y2 minus, the y is equal to y2 minus y1 by 2 is equal to y, like this also you can. So now that is y1 plus y2 by 2 is equal to y, initial value. Because this equation you want to write in terms of y means, so y is equal to y2 plus y1 by 2 you can substitute. Here y1, y2 minus y1 equal, this is the answer. So substituting in terms of y will come, y1 plus y2 is equal to y, and y2 minus y1 is equal to r omega square by 2g. So like that. So this is answer. And here volume of this parallel pipe, this volume I want to find out. So that equal to volume of parallel pipe is equal to of y2 minus y1 by 2 into area, means into 2 means here again saying area. This is volume, length into y2 minus in this half into area. So that is volume of parallel. So coming to another example. So here these two example, sometime it will take. So points, let's consider 1, 2, 3. Densities are given, heights are given. One limb height is equal to h, 3h, 4h. The length is equal to, means densities are varying 4h and 3h. So first of all, I will take this example, then I will come to here, because here densities are different. So first here limits variation and this will substitute, now you get answer. So then you can go with how to apply equations, you'll understand here. Let's consider dx in the distance x. So dx element in the distance x from this one. You can take here also, no problem. This side also you can take dx element, not a problem. But I'm, for my convenience, I practice like this, so I'm taking like this. Dx to take here. Total liquid is same density. Therefore, Pa is equal to H rho g plus P naught. Pc is equal to H rho g plus P naught. That means Pa plus Pc is equal to 2H rho g. So you can go with this is 3 and 1 like that. So 2H into rho g. So now here, because of this rotation, So this is the C point, B point and A point. So about the B point, this tube is rotating with radius x. So now x is varying to this side h and this side 2h. So the variation of limits of x is equal to the remaining and all common. Limits of h is equal to 2h to h. So therefore pressure difference, here pressure difference, the right hand side more pressure should be P plus dP. Therefore pressure difference dP is equal to, the rho omega square x dx. So after substituting already, after many problems, I am telling. Therefore that is equal to P1 in here, P1 means H to P1 to PC. That means PA to PC dP. Limits have taken 2h to h. Therefore h means PA, 2h means C, right? So h means here. So that is PB, sorry, PB to PC. So now that equal to rho omega square integral h to 2h x dx. So that equal to PC minus PB is equal to rho omega square into here 2h whole square means 4h square minus 3h square by 2. So this is one equation keeps away. So here h integrations are 0 to 2h means PB will come. Here this is PA only, PC minus PA. Right. So already I got PC minus PA this value. Now here omega and here h rho g are the PA plus PC I got one equation. And here another equation. This is 2 and this is 1. Now let omega is equal to the root over g by h. That implies omega square is equal to g by h will come. Now substitute here PC minus means PC minus PA is equal to how much will come in terms of h? Substitute g by h means 3g h by 2 into rho. So g by h is substitute now will get 3g h rho by 2. So this is equation 3. So now 3 and 2, 3 and 1, 3 plus 1 I am doing. 3 plus equation 3 and 1 I am doing. PC plus PA is equal to I got already 2h rho g. So now subtract now. Adding means 2 PC is equal to, so this is 7h rho g by 2, right? 7h rho g by 2. So that implies PC is equal to 7h rho g by. So now this PC substitute in PA, you will get some other answer. So I hope you got answer this. And if you want to P2 also, you can find it. So this is already Magnum time, you can solve it. Now coming into this problem. So here two ways I have to do. First, this is density rho is given, so you take dx element here. And integration of, so similarly dP is equal to same formula, the rho omega square into x dx. So this is equation. Here integration of x is equal to 0 to 4h. So then you will get the pressure difference between 1 and 2. So that equal to P1 to 2 I am doing, P1, P2 minus P1 is equal to the rho omega square into 16h square by 2, that equal to 8h square. 8h rho omega square. So now here P1 I know h rho g, so it will go that side. P2 is equal to h rho g plus 8h rho omega square. So this is equation 1 key. Similarly, so here you take dx element in the 2D from the x axis only, x distance from axis only you have to consider this also. Then the pressure difference in the pressure is equal to, difference in pressure is equal to, you will get the rho omega square, 2 rho omega square into x dx. So now integrations of again 2 2, the 2 to 3. So P3 minus P2, 2 to 3. So here only the integration of xr varies from 4h to 7h. Therefore in 2 rho omega square integration up to here only, P2 only we are finding. So this x value of here and 1 and 3, that equal to 7h, 4h to 7h. So that equal to 2 rho omega square into 49 minus 16. 33, 49 minus 16, 33 h, right? H square 33 by 2 into x square by 2 h square. So that equal to, here also this is h square will come. So x square by 2, then h square. So that equal to 33 rho omega square h square. This is equation 2 will consider. And here P3 is equal to, I can take P3 is equal to 3h rho g, add that side 3h rho g, that is here P3 is equal to 2 rho into 3h, that equal to 6 rho gh minus 33 rho omega square into h square is equal to P2. So this is equation 3. So now from 1 and 3, from 1 and 3. So these two are equal, P2, right? Therefore, 6 rho GH minus 33 rho omega square H square is equal to H rho G plus 8 rho omega square H square. So now H rho G bring this side, send that side rho omega square. So now 5 H rho G is equal to 41 the rho omega square H square. H get cancelled. So now he's asking omega value or H value, whatever you can find out. The omega is omega square equal to the rho get cancelled 5G by 41H. The omega equal root over 5G by 41H, or H is equal to 41 omega square by 5G. So whatever is asking to find, you can find H values. So this is related to pressure and their concept. Thank you. I hope I have given maximum clarity. So if you want to means you can comment any doubt. I will explain that point. Thank you.